Those are going to be up near the beginning. But any questions you guys have? Any things you've been wondering? Yes. Yes. Let's see. I was hearing some whispering of that. Let me remind you. It's on, of course, the Maine University's scheduler of when final exams are, because they set them for everybody, not me. It's on our schedule on WebAssign. Yeah, it's Monday, May 4th. May 4th. Fortunately for you, it begins at, well, it's similar. It overlaps our class period, but it starts at 10:30. 10:30 for 2 hours, 12:30. It's right here, though. So Monday, May 4th at 10:30, right here. We can have the final. I've chosen, I finished writing it 2 days ago, minus 4 questions, because we haven't finished that material yet. But they're the same exact style, and from the same pool as before. There's just going to be 60 questions total, which will cover everything. Yes? With the final, you will not be able to retake it because class will be over. So the final is a one-shot thing. I am still grading the superhero papers. Each paper takes me, probably about, all in all, I don't know, I'll round up to 30 minutes. So I'm enjoying them. I haven't run across that's not fair. There has been a couple bad ones, but most of them are pretty good. Most of them are pretty good. I'll admit it's easy to tell those that put forth effort and those that didn't. and then it's just the details of how much physics is in there. So that's what I'm hashing out. Following my scoring rubric, so you'll be able to tell, oh, I got this many points out of this, and you'll know what it was for and whether you got the points or not. Other questions? All right, let's log in. Got some review questions. Let's see how we're doing on this, you and me, on this electrostatic stuff. We've introduced it to you. Got a good foundation going anyway. But let's see. You've heard it once from me. All right, question 1, I'll go ahead and open while some of you might still be logging in. You got a neutral atom with 22 protons. So how many electrons are there? So that's your friendly reminder too. There's your source of the 2 types of charges. What's it mean to be neutral? Oh, yeah. While you guys are still logging in, first one always takes longer. I'm going to write 3 device ID numbers, again, on the board. I've emailed the whole class, but it's been a while since I've reminded you. There's still 3 device ID numbers that are turning in responses and not getting any credit because either the registration process didn't work or you did it incorrectly or you haven't done it. Unfortunately, too, one of these I can tell have been here and answered almost every time. So they're coming to class, participating, think they're getting points, but they haven't told me what their device ID number is. Friendly reminder that for your clicker, it's on the back side of it. If you did ResponseWare, you got emailed your ID number. Encourage you to at least double check if you're worried, especially this one. This is the one that's getting points almost every time, but you're not going to get any credit for it until I know who you are, because it has no name associated with that ID number. Which will be easier to see, obviously, when the lights come on. But all right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, that's good. All but one of you had answered. Overwhelming majority of B. Very good. Neutral means you're balanced. I like this question because it emphasizes that there's charges in everything. Neutral just means they're balanced. Positively charged means you have less electrons there, and vice versa for negative. All right, go. So Coulomb's law defines that force. What happens to that force if the charges are brought closer together? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and most of you D. So you got increases, B, or increases only if the charges are of opposite signs. The correct answer is, drum roll please. Thanks. B. D is in the denominator. It's inversely proportional to D squared. You remember that? Coulomb's law. Force is inversely proportional. If you get closer together, it increases. Period. The force. If there are two negatives and they get closer together, the force increases. The direction of the force is going to be in which direction? Repelling. If they're both positive, they'll repel. But if you get them closer together, the force is going to be greater. They're going to repel with greater force. It still increases. If they're opposite, they're attracting, correct? But if you get them closer together, that attractive force will increase. So it doesn't matter the charge, the sign. Coulomb's law says if they get closer together, the force will be stronger by 1 over D, or by D squared. This is how much stronger it will be. If you go apart, it'll get weaker by D squared. All right. Got this cloud in the sky that's negatively charged on its bottom, positively charged on its top. This cloud moves over a section of ground. What's it going to do to the charges in the ground? Negative on the bottom. Yeah. Can't tell, I'm a visual person. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you think B, but not as confident. B's have it though. That's called polarization. It's going to influence the charges in the ground. The ground is neutral. It's got positives and negatives, right? Does that make sense? So these negative charges are closer to the ground, so the force is going to be stronger. What do negatives do? Repel other negatives. and attract positives. So it's like you'll end up with positive charges coming up. You get the idea. Where the negatives will get pushed away. They rearrange themselves. That's polarization. It's like the balloon on the door. The door's charges got rearranged because they were influenced by something charged near it. Don't get me wrong, the positives influence too, but they're farther away, so they have less of an effect from Coulomb's law. Yep. So what we're doing is building up a big difference in charge here. And if it's big enough, also, there's an electric field established in here while I'm on it. Which direction is the electric field? Do you remember which way it goes? If you can't, you put in a positive test charge. Let's put in a little positive test charge right there. Which way will it go? Up. So that's the direction of your electric field. Wink. That way. Wink. Wink. That's your electric field. It goes away from positives towards negatives. And if that electric field gets high enough, whammo, it'll actually break down the air. It'll ionize them. Ionize means you turn them into ions. And an ion is an atom that is no longer neutral. It's removed an electron or gained an electron. If it is no longer neutral, it's conductive. It's charged, negative or positively. And if it's conductive, whoosh, this charge tries to equalize, neutralize itself to get from here to here, here to here. And that's the lightning bolt. Yes. Lightning goes up from buildings. And if you ever watch those slow-mo cameras, you get these leaders that come down, and we often think lightning strikes down. What we normally think is the main lightning, it's actually going up. They can even come in the middle. They can go from cloud to cloud as long as there's a big enough difference in charge. So this one, I don't know if I ever actually mentioned Coulomb. So I'm doing it now. The unit of charge is Coulomb. A unit of charge is a Coulomb. And I don't know if you guys will get this one. This is my teaching moment. So 10 newtons of force to hold this tenth of a Coulomb particle at rest in an electric field. The strength of the field is, and I know you guys just got exposed to this. Here's your reminder. We had F equals ma for Newton's second law. That was for gravity. You got this gravitational field that accelerates the masses. For electrostatics, it's the charge you're trying to move in coulombs. And what's causing it to accelerate? The electric field that's established. So another way you can look at this is electric field is the electrostatic force over the charge. I tell you that because your answers are in newtons per coulomb. Force is in newtons, charge is in coulombs. There's your electric field. The answers are the strength of the electric field. See, I'm walking you through it here. If it's 10 newtons of force to hold it, and you have a tenth of a coulomb, what's 10 divided by a tenth? 10. Give you 10 seconds to find out. 9, 8, 7, 6, 5, 4, 3, 2, 1. C of 100. That's right. That's right. That's how you can use that equation to figure out the strengths of these fields. Or if you knew the strength of the field, you know how much force it would take. Or how much charge. You know, one or the other. Does that make sense? Again, this might look foreign and new. I try to relate it to this so that, you get a cheat sheet, right? But beyond, you leave the class. It's analogous. 24. That's the next one. All right. In the electric field surrounding a group of charged particles, for example, you can look at this one. I haven't drawn them all, but all the electric field lines. The field strength is greater where the field lines are what? While you're thinking, I'll draw in some more here. The field lines tell us something about the strength of the electric field. These aren't answering as fast. So I remember I drew some field lines over here before. You guys, your gut was right. I asked, where do you think the force or the field's the strongest? And that happened to be where the electric field lines were this answer. If that helps. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're missing a few folks. D, closest. Good. That's absolutely correct. So the electric field line here would be near the tall building. Your gut probably can tell you that. It's closer to the clouds, right? There's less distance covered here. So yeah, the electric field will be stronger right here. And that tall building's more likely to get struck by lightning than something else. And you can visually see that. It's kind of like you got an electric field line trying to go up. But it's closer to here, so it's just going to curve from there. Something's got to go out, it'll go to the clouds. So field lines are great to visualize things if you're having trouble. Oh, there it is. One more. The electrons on the surface of a conductor will arrange themselves such that the electric field is what? So remember, on a conductor, they're free to move around the flow. How will they arrange them? They'll arrange themselves in such a way that the electric field is what? I just write down Coulomb's law while you guys are thinking. That's our friend. That's our friend. All right, how are we doing? 10, 9, 8, 7, 6, 5, 4, 2, 1, 0. Oh, no idea. Okay. Guess that's because it was the very last thing I did at the end of lecture, and people's brains wane throughout the lecture. Well, the correct answer is inside cancels to 0. That's the shielding. Turn the lights on. Actually, no, I'm not. You can put your clickers away, but I got something on there to show you. Apologize for that if I threw you off TLT. Remember that it's called a Faraday cage. I put the radio inside a cage, and the electric field gets to the metal conductor, and it influences the charges in the metal. They have charges, and the charges arrange themselves such that the field completely cancels out inside. If you're inside, you see this charge on this side, but you also see the charge on this side, and they both affect you, and they cancel out. If you're closer to one side, this will be more of a force, more of an influence. But you're closer to it, so the cross-sectional area of charge is less. And that balances. So you're closer, so that makes it stronger, but there's less charge influencing you than over here. You're exposed to a bigger cross-sectional area. So more charge, but it's farther away. And they balance to cancel the electric field inside a conductor. So, back to lightning. If you're in your car and you get struck by lightning, which happens too often, you're protected. The car is a metal conductor and shields you from the electric field inside, mostly. And most people survive lightning strikes if they're inside their car. Not the best place to be in a lightning storm, but it can also conduct it around and into the ground, not through you. However, be warned, your car could be charged now on the outside. So people, after the cars get struck, they open the door and step out. And what do? They just make a connection between ground and the outside of the car. Boom! Oops. So if you get struck inside a car, jump out or stay there till someone helps you. Oh, I was going to mention too, your microwave. Have you ever noticed the metal grid? You can look in, but there's a metal grid there. Have you ever wondered what that's for? It's not for strength, so the glass doesn't break. It's creating a cage. The oven's a big metal conductor, but the door isn't. So they line it with the grid like our cage. And it's keeping the microwaves that are cooking your food, the electromagnetic waves that are cooking your food, from getting out. It's shielding you, kind of like an inverse cage. You know? Yeah. What would cause a microwave to knock out Wi-Fi? The power supply that runs it, powers it, emits electromagnetic radiation. All power supplies pretty much emit electromagnetic radiation, especially ones that are alternating current. So you haven't got to change its direction. And it's that change. They emit electromagnetic waves. That's what influences and messes other things up. Generally, the bigger it is, yeah, or the more powerful, the more energy it can output, the more it can influence other electromagnetic devices near it. It's like if you're near a radio station, the actual station, the tower, you're going to pick that one up great. But your favorite one way over there is going to get interfered with by these waves. And you won't be able to pick it up as well because this one's dominating. Similar idea. All right, found some few animations here. This one, if you bring this rod that's negatively charged up here to a paper clip down here, watch what happens. Gets a little closer, gets closer. The electrostatic force is based on distance squared, so it doesn't act over really long distances. You got to get close. So a little closer. There. Now, as it gets closer, see what happens to the charges in the paper clip? The paper clip's still neutral, but it rearranges. We call that what? Polarization. You can see the positives are attracted, the negatives repelled. Let's do it one more time. Now that you know what you're looking for. So let's use that. Let's bring this negative rod near this ball. What charge is the ball? Neutral. Good. There's the same number of positive charges as there are negative. Let's bring this near. Oh, I guess we play this one. Watch. It comes near, and look, it polarizes them. Reset. Before they touch, it polarizes the charges in the ball. See them rearrange themselves? Now, since they rearrange themselves, this ball is free to swing. There's an attractive force between it and the rod once it's polarized. Those positive charges in the ball are attracted to the negative charges in the rod, and so it pulls them together. Coulomb's force. Then they actually touch. Boom. Do you see what happened to some of the charges on the conductive rod? Watch the charges on the rod once they touch. If they're in contact, you can charge the ball by conduction. And some of those charges are physically transferred over. Now what charges the ball? Negative. So it polarized it. They were attracted. It was free to move, so they did. They touched. Charge was transferred through conduction. And now they repel each other because they're both negative. Yeah.
I'm trying to picture like polarization. So the neutrons and the electrons are spinning around each other, right?
Yeah.
So as they get further apart, are these neutrons just, or the electrons spinning?
Yeah, it's not a perfect analogy, but yeah, you got that atom with a nucleus and charges. Essentially, instead of being nice and spherical, maybe it gets oblong. And so this side will have more of the positive charges, and the electrons will spend more time over here, in this part of the atom, on average. And so it's as if there's a negative charge here and a positive charge here. It's just kind of shifted. It's been polarized instead of just overlapping and being all pretty. So you can influence this side by being closer to it, or this side. And I think I had one more. Yep. Similar thing here. So we're going to bring this negative rod into these, A and B. Watch again. This is charging by induction. Notice the rod never physically contacts the sphere. It comes near it, influences the charge in the sphere, sphere A. You see these charges rearranged. Note that again. They come in, see how they rearrange? But sphere A is connected to sphere B. So where do those charges go? Onto sphere B. And now we've charged those spheres through induction. Induction. So that reminder of those two. Does that make sense? That help? Now we can finally turn the lights on. Oh, good question. Why do the spheres move apart? That's not because they're free to move. They're on the table. There'd be too much friction. So this is like somebody grabs sphere B after that and moves it away. That was like me touching the electroscope we had. I brought my rod near it. It influenced the charges. Then I'm like sphere B. Charges left. But then I removed sphere B. So yeah, that's someone would physically have to move it. You guys have a better foundation for charges and forces between electrostatics than the majority of the population now. We're going to start moving them. Where are we at? Okay. Electric fields, we got that, got that. All right, now that the lights are on, if you haven't checked your device ID number, please do so, if you want credit anyway. Okay. Where are we at? Where are we at? New term. Electric potential. Electric potential. That's the same thing as voltage. That you've heard of, right? We use them interchangeably in this course. Your book explains that too. So potential might be a tip-off. It has something to do with potential energy. You're right! So let's do our analogies again. Remember if you had a mass and you want to get it up here onto this ledge, a certain height up. We're in this gravitational field. All right, we want to get it up there. What do we have to do? Work. Exert energy to get it up there. You now know it's called work. Work, who remembers what it is? It's your review for the final. F what? That's right. I heard it too. Good job, Stephen. You're right too. Force times distance. We exert a force on this and we'll move at that distance. What's the force we have to exert for that distance h? Well, gravity's pulling the mass down with its weight, so we have to overcome its weight. So we at least have to pull with its weight. mg. Recognize that? mgh? That's our change in potential energy. You do work, energy is conserved, so once it gets up there, it now has mgh of potential energy. gravitational potential energy. So basically, we were moving this mass, this object, against the field, the gravitational field. To do that, it naturally wants to go downhill. So to lift it up, we got to put energy in. It'll take work. There's our analogy. Let's apply it to electrostatics now. Let's say we have a charge, and we want to get it up here. Distance d, pull it away, and what's our field? Electric field. Notice I made it a positive charge because it would want to go downhill, right? Positive charges go in the direction of the electric field. So we do work. It's still force times distance. Everything I taught you doesn't go out the window. The force is now what, though? It's our mass. We're not dealing with the mass of an object. We're dealing with a charge now. So we use Q. And what's accelerating it? Not the acceleration due to gravity, but the electric field. So we put in QED here, or QE, and we get QED. That's the change in potential energy, but the electrostatic potential energy, not the gravitational potential energy. So that's another guide to your thinking, if you want to note that one. But the point is, it takes energy to move a charge against the electric field, a positive charge. You know this. If you have a positive and negative charge, they want to attract. If you now want to separate them, you're going to have to apply a force and exert some energy. Do some work to do that. This is how much. It's based on the amount of charge in the electric field you're pulling against. Now where it gets a little different is, instead of dealing with objects, single objects like we did at the beginning, it's kind of like our fluids. There's lots of little particles now, and it's hard to keep track of all of them. There's lots of charges. We don't want to keep track of all of them. So they create this term called voltage. And what is it? It is the energy per charge. You've heard of voltage probably most of your life. It's the energy per charge. So we don't have to differentiate all the little charges. And voltage is technically the electric potential. What's the electric potential of that situation? Well, let me tell you how much energy per charge there is. So when you hear something 120 volts, that's the voltage. That's how much energy per charge there is of something. See what they do? If you divide this side by Q, it goes away over here. And you divide it over here. There's your energy per charge. That's the voltage. That's the electric potential. What is that? It's ED. Or some people like to remember it this way. I know, I'm putting boxes around lots of things. So there's two ways to think of voltage. Energy per charge, but it's also an electric field for a certain distance, because we deal with electric fields around these charges. Hopefully the rest of this lecture will bring some light onto that. I mean, you're like, yeah, so what? How do we use it? One more analogy. Voltage is a lot like temperature. You know, I made a big to-do about the difference between temperature and heat. Heat's the energy transfer, has to do with the energy. Temperature was a measure of the average translational kinetic energy per molecule. Let's just sum that up. Temperature. This has a certain temperature. So that means, on average, those particles have a certain energy per particle. That's what the temperature tells you. If you heat it up, the temperature goes up. That means there's more energy per particle. So energy per particle. Voltage is the same thing. It's energy per particle, per charge. So if that can help you. Remember, we had sparklers Sparklers were really hot. Lots of energy per charge. Temperature's high. But there weren't that many little particles. So there wasn't much energy there. It didn't give off much heat. It didn't burn us. Similar with voltage. You can have something that has a really, really high voltage, like this. This, on a good day, it'll be 3 to 500,000 volts. Turn it on. We charged it up. Ooh. Sure, it shocks you. It surprises you. But I'm not dead. So it has a lot of energy per charge. High electric potential, high voltage. But there aren't that many charges there. It doesn't push that many charges around, so I don't die. That's how we use it. Do another example. Let's see. If we had 1, 2, 3, 4, 5, 6, let's say, and one over here. So one charge, a lot of charge, and they're this distance away. I guess while I'm talking, you can see it better. So which way is the force? Between the two? Yeah, they repel. We'd figure that out with Coulomb's law. You could plug in that constant, the one charge, the other charge, and they're this distance away. That's the force. That's the force this one feels, and it's the same force this one feels, right? Newton's third law. If we tried to bring them together, that would take work. We'd be going against the electric field. That would require work. Let's look at that electric field. It was, what? Here we go, I want this one. No, I don't. No, I don't. Not yet. Let's look at this one. That one. That's the electrostatic force per charge. Because we're looking at the force on these charges. That's what I want. All right. There's a certain force. And there's a Q. That Q would cancel that Q. It comes out to, I'll spare you, that. Something. All right. Now let's change things to compare. Let's have the same charge here, same distance away, but now you have two charges over here. How does the force vary? We just doubled this charge, nothing else. How's the force vary? Distance is the same, big Q is the same. The only thing that changed is there's two of these over here now. Will it take more force to push them together? You're nodding your head. How much more? It'll double. See, it's K, that charge, but now we have 2Q E squared. So it'll take twice as much force. They're feeling twice as much force because there's twice as much charge. I hope that makes sense. But let's look at the electric field. It's force per charge. We've doubled the force. There's an extra 2 here. But we have twice the charge too, don't we? So something that's neat with electric field is it doesn't change. We would say the electric field between these two charges, objects, is the same as the electric field in there. Which means the voltage is the same. The electric potential between them is the same. Because that is, if this didn't change and this didn't change, that's where this comes in handy. I think you know that you add more charge, there'll be more force. That makes sense. It's like if you add more mass, it's going to resist you more, and you need more force. So there'll be more energy involved. It'll take more work to move those the way they don't want to, just like if you double the mass and lift it up. And once you get up there, you'll have twice the gravitational potential energy. Same with charges. But we don't like dealing with all the individual charges. It gets really annoying that, with the thousands and millions and billions of charges in here, if we gain or lose one, we don't want to recalculate everything. And it's convenient to have these terms electric field and voltage, electric potential. They don't change. Because sure, the force changes, but so does the charge. So this energy per charge, this volts per distance, the electric field, don't change. That's why we can plug into the outlet that's 120 volts. But you can plug all kinds of things into it. And it can still have a similar influence on your different circuits. Even though there's a whole bunch of different setups and conditions and charges, it's still 120 volts for both. The electric field that gets established would be similar. Does that make sense? That's probably, I think, the hardest thing to wrap my head around in this week. So let's do this one. Let's not kill someone. Would someone like to try it? You probably got the idea. Come up. We'll charge you up. And your hair can stand up. Yeah, come on up. While she's coming, let's see. Let's put it about there. So it'll take a minute to charge her up, but that's what we're going to do. We're going to insulate her from the ground so charge can't leak off of her. Oh, that's nice. And we're going to have, but I don't want you that close to the table. Because we don't want to give a path away from you. There we go. Go ahead, put your hand on there. You can do both or one, doesn't matter. You comfy? Okay, I'm going to turn it on. This will not hurt you. If you don't touch the table, you're going to get charges moving on to you. If you give them a path to leave by touching me or touching the ground or this, they will. And that's when it'll hurt you. I mean, you'll feel the shock. It won't kill you, not that kind of hurt. So don't let go, don't step down. All right. The way this works while we're waiting is the belt comes off the pulley. The objects separate, right? We did that with the balloon and the fur and the rods, and every time the tape off the roll. When it comes off, charges separate. Long story short, they get stored on the sphere. The electric field inside the sphere is what? Inside. Zero. The charges go on the outside. She's touching the outside, so they move onto her. They're all the same charge. Do they attract or repel? Repel. So we get into her hair and they try to repel each other. It's working great. Or well enough. Yeah. All right, don't let go. So now they're still at that electric potential. They're charged up to several 100,000 volts. She has an electric field around her. If I were to touch her right now, I'm at 0 volts. I'm grounded, I'm neutral. If I were to touch her, the charge would rebalance. It would flow, and we'd both feel it. You can step down now. There, did you hear that?
Yeah.
So please give her a hand. That was brave. If you ever feel like that outside when it's looking stormy, take cover. That's bad news. I mean, that's getting like this. The electric field's building up because more and more charges are coming to you. The electric field goes up. There's a higher voltage, a higher potential difference between here and here. And if that gets too large, whammo. Just like temperature. Where did I write that? Up there. Heat, energy didn't flow until there was a difference in temperature. Remember that? It didn't matter who had more energy. It mattered who was hotter, from hot to cold, high to low, change in temperature. Same here. Charges won't flow until there's a difference in voltage, electric potential. If they're at the same potential, they could both be at 1,000,000 volts. Nothing would happen because there's no difference. But if she's at 200,000 volts and I'm at 0 and we connect, that's a big difference. They'll flow and we'd feel it. I bought this just after Christmas. Anybody recognize it? Yeah, the Monster High Frankie doll thing. I had never watched this show or movie. But anyway, it's a little doll. But it's great. It's a toy. She gets recharged. It's like supposed to be Frankenstein's daughter. Frankie. But she goes in this chamber and recharges. There's a Van de Graaff generator inside. This is a Van de Graaff generator. There's a little belt and pulley back here. I took the whole thing apart. And so if you hold this button down, it's just like you. Charges build up. It's great. I love it. It's a little Van de Graaff generator. And this was a lot less expensive than this was. There you can see the hair follows the electric field lines. If her head's negative, see how they radiate all around it? If it's negative, they become in this way. The field is this way. If I touch her, you see how they influence? See the field lines? And I can remove all the charge if I want, but that's not as fun. So. This that I used briefly before is a Van de Graaff generator. Again, there's a little belt in here, separates charges, charges this up, and if there's a big enough charge, the electric field will be high enough, and it'll influence the charges in this mylar film. So I charge it up. This should fall. It touches this. It's getting charged. It's getting charged the same, and they repel. I can levitate it. The electrostatic force is now balanced with its weight because it's not that heavy. You can repel. Wingardium Leviosa. No, it's Leviosa, not Leviosa. I don't know what it is. If I bring my neutral hand near it, what will it do to my charges in my hand? Polarize them and attract. Then it touches, neutralizes, falls back down, gets recharged, we can go back up again. So this is called a fun fly stick. It's about $25. Fun fly stick. But it's a Van de Graaff generator. Separating charges, creating that electric field. It gets up to a relatively high voltage. So the voltage is high. A lot of energy per charge. But there aren't that many charges, so we're safe. Let me just do one more because I don't feel like setting it up again. And we'll leave on these. The electrostatic field can be enough to lift those off, repel their weights. Packing peanuts. All right. That'll work. Take care.